All right, folks, it's Bass Action back in action here. This video is going to be significantly shorter than the one that we did for the perpendicular bisectors because there's not quite as much happening in this one. This time we're going to look at our angle bisectors, and just like before, we've got all three types of triangles. I have an acute triangle. Yours has probably already been labeled with a nice right angle there for our right triangle, and then we've got our obtuse triangle, okay? So just like before, we've done angle bisectors, but now we're going to look at angle bisectors inside a triangle instead of just as a single angle. So an angle bisector, just as we've been doing before, is going to be a segment, could be a line or a ray or a plane, that's going to bisect, so it bisects an angle. Just like before, all three angle bisectors will intersect at a single point. That's called a point of concurrency, and the point of concurrency for the angle bisectors is called the incenter. Now, if these are in fact angle bisectors, which these have been constructed to be so, then we would have a pair of congruent angles, another pair of congruent angles, and a third pair of congruent angles. If the triangle is not isosceles, then you don't know that those are going to be equal to each other. Now, on our next one, we've got a pair of congruent angles, but if this is a right angle and it's being bisected, you could, in fact, remind yourself that these are both going to be 45 degrees. It's the only time you're going to know the actual measure. Then I've got another pair of congruent angles and a third pair of congruent angles. Same deal on the next. I've got a pair of congruent angles, a second pair of congruent angles, a third pair of congruent angles. Notice that the congruent angles are all that we get. We don't know anything about the sides of these triangles. Now, I said that this point of concurrency is called an incenter, and the incenter is going to be used to inscribe a circle in the triangle. Now, when we measure the distance from the incenter to the side, that's going to be our radius for our circle. That must be done on a perpendicular. We're going to do this in class. I'm not going to do that here in this video. If you want, you could certainly Google it and find it out, but we're going to do it together in class. Now, the next thing that we're going to do is we're going to look at just a couple little theorems here. These are very similar to the perpendicular bisector theorems that we did, okay? An angle bisector theorem says that if a point is on the bisector of an angle, then it is going to be equidistant. Now, we've seen this word before in the last video that we did. Okay, sorry, that's supposed to be a T. Equidistant from the sides this time. Now, the perpendicular bisector was equidistant from the vertices. The angle bisector is going to be equidistant from the sides of the angle, okay? So, for example, if HU is an angle bisector, of course, we know that those two angles are congruent. And then if these little segments here are indicating the distance to the side, these would be right angles. Yours might even already have the right angle drawn in on it. If I am telling you that DO is 5 units, so if DO is 5 and HN is 6, and we wanted to find the length of HD, what we would know is that if this is on the angle bisector, then this 5 should also be the same as right here. This should also be 5, okay? That means that we can work with this little triangle here that's going to make a nice right triangle for us, and we can just do a quick little Pythagorean theorem. So an x squared and a 25, which was my 5 squared, and my 36, that was my x squared. So x squared is 61. So the length of HD is going to be the square root of 61 units. So it's going to be a little bit less than 8. Now the converse is also going to be true. So if a point is in fact equidistant from the sides, so if it is in fact equidistant from the sides, then it is going to be on the angle bisector. So if I look at this figure and I tell you that HG is congruent to UG, so if these two are congruent, then this would make a nice right angle here and a right angle here, and then that would mean that SG is an angle bisector. Now, we could even go on then and actually prove that these two triangles are congruent. So that's kind of how we would prove this theorem if we wanted to. But for the most part, I just want you to know that these two segments, when we've got these nice right angles here, if those are measured on the perpendicular, that they will be equidistant from the sides of this angle if you have an angle bisector. Okay, that's all that we've got for angle bisectors. That's a pretty quick and short one. And then we've got 2 more segments to do in this chapter.